I have this typed value be repeat, and I want to serialize it or compress it while still being able to recover the original value. This is about Pickler combinator, a great concept by Mr. Kennedy, and it's used in many languages, in Haskell, ocaml, JavaScript, whatever, you name it, Python, or whatever. The concepts are entirely general. That said, let's dive into the Haskell implementation, which is provided for us by the paper. So the first thing to notice in this implementation is that it's divided into a core library, which provides the basic instruction, and some extended library, which uses the core library and is just here to provide some additional sugar for the user to make it easier to adapt to real-life data structure in a way. So if we look at the core library first, the most important operation is this pickle and unpickle pair of operation that will take some data type PUA, and given that data type PUA, which describes in a way the format of A, provides a pair of function pickle from A to string and unpickle from string to A. Now, as you can see in Haskell, we have the list of implementation below in a file, and at the top we have module core pickle and the list of exported functions. So those are the visible functions from the outside, and you can see that PU does not have any constructor exposed. It just has the type. It's just a type, the existence of a type, so it's completely abstract from the outside. Now, given the fact that we have as main functionality this pair of function, as an implementation of PUA, which is an abstract type from outside, we have also a pair of function. Now that pair of function, as you see, is some A to string and string to A, but with some extra state for the first one and as an input, and extra state as an output for the second one. So we use these functions to plug in to conform to this interface. So given some PUA, which describes the format, given some value A, we call app so that will extract the first function, the first component of the structure P of type PUA, and feed it a value of type A and an empty list, which is our type string st, which is equivalent to string in Haskell. And likewise for unpickle, we, given the format P and the stream, we extract the second component of the structure of the format, and we feed it a stream, which is a string, to get back the answer. So this is the most easy implementation. Now let's look at some basic combinator, and the most interesting one is lift. Now lift, you can see that it takes the function second, and the function that takes a state and gives back a tuple x and that state. So you can see that it conforms to the type PU. The interesting thing is that it ignores, if you see the first one as a pickle, pickle goes from some value A to string, it ignores the value, and it just returns the state unmodified. That might be surprising at first, but this is really the essence of Pickler, because when we have a type PUA, so this describes the format, and the fact that we do ignore the input means that all the information is already there. It means we have a more static choice in a way. The information is already in the format, and so when we decode, since we didn't add it as part of the stream, we shove it x as a first component of the tuple, and x has been given as part of the argument of left. This is really where x comes. So lift says, in a way, I already know the next step. And this is the goal. We want to upfront, we want to make it already known, everything that we know about the type all around this library. So we can see it at work. If we are defining L as a core pickle dot left and some value, okay, and if we give it, we say pickle L, so that we describe a format and some value 9, it stores nothing. You can see that we have an empty string as a result. So it didn't store anything because everything is actually stored in the format. And when we unpickle the empty string, we will get back the original value, 545, etc. And that means that's because we've stored our knowledge inside this format. Below base, just transformed some integer into a character, because st is a list of a character and we should give back at p a string. So 2nm will go from integer to character. So we choose base for as a reference, which stores 2 hexadecimal value. So when we decode, we go from a character to an integer using the function from enum. Now the most interesting function is this function sec. It first takes an argument from B to A. The goal is to produce a pickler for the type B. So we want to describe statically as much as we can of the type B. One strategy to do so is, if we have a function f, we can describe it in sequence in a way. So since we are to we have a function from B to A and a way to store the any type A, and a function from A to P, pu of B. That is, K is selecting a pickler for B based upon a specific value of A. Now, what's the implementation? We have to produce a pub, so we have to produce a pair of function from bst to st and another from st to bst. So the first one goes from bst to st, so here it is. So we start with a b and a s. Here we extract the knowledge, we extract some knowledge from b, some partial knowledge, and a represents this partial information. Now with this partial information we use this function k, which is a deterministic choice for pu of b based upon a value, a specific value of a. So we select a specialized pickler with this information. And now we will encode b with this specialized format. And after we've encoded b, we will store a using this format PA. And so the information for A will be before in the stream, it will be prepended. So when we decode, we first decode A using PA. And now based upon that A, we will use this deterministic choice, which is represented by K, and we will feed it the value A. A appears first. Now we use A to select the pickler, and of course we answer back the state using that specialized pickler. So this reading of sec as a partial serialization in a way, a partial integration of information is a very fruitful one, and we'll see that all across the library. Now, this defines the interface here, and how do we use this interface? How do we use this core pickle? You see that we have many functions here that all use this core pickle. Now, the first combinator, sugar combinator that we can define is pair. So it takes two pickler, PA, PB, for the type A and for the type B, and it builds a pickler for the tuple AB. Now, how could we store a type tuple AB? Well, if we use sec, you remember that the first component extracts some information. So we use first. First, we'll extract an A from the tuple AB. We will store that A with PA, and given the value of A, we will select a new pickler for AB. And what will this pickler be? It will first extract the information in the second component, store it with PB, and based upon the value of that second component, it will give back a lift AB, which stores as part of the format the value AB. So it's part of the format. It doesn't need to know, except that we've composed it with sec AB. So at some point we have to provide A and B, but we've explicited as much as we could in the structure of AB. And one important point is that this value A is not used for selecting PB. I mean, this is a static choice, and it's we've encoded that it's completely independent. We don't use a function from A to PB for selecting PB. We use it to build a new pickler for AB. So of course we have the same strategy for triple. So we project out, we extract some partial information from this triple into X, and then we store it, and then we build a new pickler parameterized by this value. So given an A, it will build a pickler for of signature PU ABC, and it goes on. So it extracts the second component, stores it, and pass it on a function that given a B, a value B, will select a pickler for ABC, which itself will project the third component, etc., etc. Now, one sugar extension that is very frequently needed is a wrap, which transforms a pickler of A to a pickler of B if we have this pair function provided as first argument A to B and B to A. So in the philosophy of sec, if we want to provide some pickler for B, we will extract this partial information, which hopefully is total. It's a complete information, and we will extract this information from B by applying G, which goes from B to A. We will then store the A using PA and provide a function parameterized by the value A, which provides a pickler of B. So I will receive this this A and produce a B, which we just lift into the pickler type. And here we have a unit, which is a pickler combinator at type PU unit, and you can see that it doesn't store anything in the stream because it uses lift, and it directly emits as part of the decoding stream the unit value, which is the only value at the type unit. So that really embodies the essence of those pickler combinator, which are to describe statically as much as possible the format of values at a specific type. An interesting combinator is 02, which describes as part of the format some numbers with a maximum capacity. You know, if we are to store a number, how many bits are we going to use? If we know it statically, then we can use 0 too. So of course, if we know that the maximum capacity is 0, we are storing some number, some value between 0 and 0, we already know it's 0. So we just use the combinator left, which doesn't record anything. It's already part of the format. Now, if we are storing some numbers between 0 and 1, we don't really know, and we have to apply some transformation. So we have a base case at 0, so a good idea would be to divide this number by base, and we will apply the wrap construction. So here we are applying, when we're trying to code, we will call divmod base as an input function, which will be the j function in wrap, and this divmod is the Euclidean division. So just to remember, which is not self-evident. So divmod integer, divmod something, will provide the pair of the multiple and the remainder. All right. So the static guarantee that we have is that the second part will be below the base, so we can directly use below base. The other static guarantee that we have is that the maximum capacity of the first number is less than n divided by base. So we encode that as part of the format. So divmod base gives us this pair, and this pair will be encoded using the pickler built out of pair and 0 to n div base and below base. And so an interesting thing to notice is that really, like, this function, this parameter n is part of the static description of the format, and that's why, you know, in wrap we use divmod base, which will be applied to the actual value stored, but in pair we divide n by base. We already know we are talking about n as a static parameter, whereas the particular number that will be applied at divmod base, we don't really know. It's still open n. This function j will apply whatever the value will come through. Now, once we have 0, 2, we can write Pickler for characters, which are below for ASCII character, basically, and we encode them as a particular int. And that's where using wrap is very useful, because here it's an int, and by wrapping it, we transform it into a Pickler for character by applying, post-applying and pre-applying with from enum and to enum. And you can see that we have almost the same code for Boolean, which we store as an integer from 0 to 1. And we call the same function, and the fact that it's actually the different function, it's function called at different types, is given by the type definition here, the type annotation. We do not annotate at the same type, so that the same code will produce different function. Now, a very interesting combinator is nat. Here we do not give any upper bound, and we will devise a strategy to store some number with no upper bound, except of course the integer representation, but that's not part of the definition. So we start with a value, and we will extract some partial information about x. And this partial information is, you know, is it is it less than half or not? So we will give back some value x below half if it is below half, and if it's not below half, we will explicitly store half plus x mod half, so the remainder. So we know it will be we have to multiply and take that into account. So we project this information. Now once we are here, we know that this value is below base, because half is base divided by 2. So we can store this information. So the first part will be dedicated to numbers which ended there, and the second part is dedicated to some numbers which continue. So if we are below half, then we know what to do statically. We just give back this value, lift LO, which has been given to us as an argument. So, and we can stop here. If we're in the second part, we know there is something more to do. So we don't know how many steps we will need. So we will wrap the natural number pickler. That is, we will call ourselves, but we will apply some transformation. And the transformation we'll apply is that as an input, we will take n and divide it by half. -1, and the -1 comes from the fact that we will do plus LO, and LO is this value that was given to us, and that contains already half here, so we remove 1. And upon deciphering, we are taking high as an input, and we're multiplying by half and add LO, the remainder. Now once we have that, we can look at another recursive definition, which is a pickler for a fixed list. That is, given some way to store a value of type A, given a length of a list, build me a pickler for list of A of a size given by n, by the second argument. So of course, if our list is of size 0, we just left, we already know statically that the value will be the empty list. So we encode that in the format by calling left. If we have some n, we will first take the input value, which is a list, break it down into a pair, and to store it, we will call the pickler, which results from calling pair, the combinator pair, with the pickler for the first element, A, and the fixed list called at n-1. And conversely, for rebuilding the value, we will tuple up, we'll take the tuple and build the list. Now for a list of any size, well, we will apply the strategy of calling sec, because this is exactly where we need sec. We need to extract some partial information, store that partial information, in this case the length of the list, and then call fixed list with this partial information. So it's not always clear when we can compose those higher order functions, but the type is this one. So fixed list goes from pu of A to int to pu of list of A, and then sec length nat, as you remembered, it takes a parameterized pickler, parameterized by this input value, which is the same type as the output of that function, and based upon that parameterized or specialized pickler, we'll build a pickler of that type. So we can compose those two, and we have a pickler for a list. Of course, now we have a list, we have many things. We have strings, which are a list of characters. And another idiom which comes up very often in data structure is when we have a static way to decompose a value of some type A to an integer. a deterministic mapping, if you want, from A to int. For instance, the case will be maybe, where we have two choices. So we'll have a function which takes a value and gives us, okay, first case or second case. Now, this fits perfectly well into the seek strategy, where we call tag to extract this information. Now, we store this partial information, which is an integer, from 0 to the length of what follows, because what follows, as you see here, are n independent n specialized pickler. So in the case of maybe, we will say, okay, use this alternative. I know that a maybe type can be decomposed in two cases, so use this function tag, which transforms the two cases into those index 0 and 1, and then I will give you as a list a pair of pickler, and you will choose based upon the value of produced by tag. Either you will use a lift and nothing, that is, I will know statically that this the case is nothing, or you will apply the pickler PA wrapped with, you know, from just and just to go. Once you serialize, you apply from just to extract the value A and then store it with PA. And when you're reading it, you're reading A and you're wrapping it with just. And that produces a pickler from maybe A from a pickler of A. We can apply the same strategy for either, because we have a static way to decompose a value of type either AB into two cases, 0 and 1. And once we've decomposed, provided that we have decomposed and we have distinguished those two cases, we can apply as part of the format those specialized pickler, which will wrap PA and PB with the precomposition and postcomposition by the constructor left and right and from right. So that's it for the first part. The rest will be how to specialize that, and we can see how it's being used. And the general idea is that we have those types, URL, bookmark, bookmarks, and you can see that the pickler always follows the structure of the type. So if we had a quadruple, we will have a quad, string, maybe nat, string. Then for pbookmark, we will it's a list of pair, and so we'll have a list of pair of string, and then a URL. So we'll have the pickler for URL. And once we have that, we can we have a pickler for bookmarks, and we can now say, okay, let's look at. So here I'm using stack ripple. So it's a very useful tool. I can reload, or I can exit and come back. It's already loaded, and I can look at what's inside of bookmark 1. We have this value. I can of course pickle it, and so I will get back a string of character, and those character like /SOH actually is the value 1. When you do look at from enum, it's the value 1. And so when we have B1, it's actually 1, 6, Andrew, etc. So we have this stream of character, and we can see if we can recompose. And if we look at U1, it's only computed from B1, and we indeed get back the original value that we started with. And so the wonderful thing is that we started with a typed value above bookmark, and we've mapped it uniformly into another a unique untyped, in a way, or unityped value string, and we can go back and forth between the two. And of course the trick is this format which follows the structure of the type, but is a value. That is, it's something you can actually manipulate at runtime. That's it for now, and next there are more complicated subjects about compression.